Okay, welcome back to Real Analysis. We are going to be starting our final chapter in our spring semester course here, Chapter 8, talking about the definite integral. We've surveyed a lot of calculus topics in this course. Way back at the beginning, we talked about the order properties of the real numbers, the supremum property. We talked about sequences, talked about limits of functions. We've talked about continuity, differentiability, proved lots of theorems about those notions from your experience in calculus. And now in this 8th chapter, we're going to talk about the derivative. Okay, you can see from the heading, I'm starting talking about something in section 8.2. If you haven't already done so, you want to stop this video right now and read section 8.1. It doesn't have any theorems or definitions or results in it, but it is kind of an overview of what the integral is. And it'll kind of remind you about one of its possible origins, that is computing the area under the graph of a function that's greater than or equal to 0 over some interval. All right, so I'm going to skip all of that imagery. There'll be no pictures actually in this entire video lecture. My main goal is to prove this theorem that's stated here, theorem 8.1, and it's pretty technical. I'm going to try to break the proof down into kind of digestible chunks. It's going to use a lot of the machinery that we've developed so far in this course. But I think that you want to stop the video right now and kind of take a careful read of section 8.1 to sort of put you in the integral mood, so to speak. All right, so you have some pictures running around in your head as we move through some of this stuff. Okay, so what is this theorem 8.1 attributed to Koshi? Well, its preamble will take a couple of real numbers, a and b, one less than the other, and a continuous function on the closed interval from a to b. And then the theorem is saying, it's heart of it, it's saying that there's some number I that has some properties. So the theorem is saying that there exists some real number I, such that no matter how you pick a positive number epsilon, there always exists some positive number delta. So for every epsilon that's greater than 0, there's a delta. So that, and I'm going to kind of skip to the bottom here, whenever you pick a sequence of points between a and b, strictly increasing, with the first one x0 equaling a and the last one xn equaling b, there can be any number of them. Okay, so whenever you pick such a sequence with the property that the distance between any two consecutive ones, that is xk minus 1, is no more than delta, and you choose some points, this is the Greek letter xi sub k, it's subscript because I'm picking them in that kth subinterval between xk minus 1 and xk. Whenever you make such choices, this sum that's formed by plugging those xi sub k's into f and then multiplying it by the corresponding width of the subinterval, xk minus 1, that sum differs from I by no more than epsilon in absolute value. Okay, so if you read section 8.1, you kind of recognize this. If f is non-negative, then you can think of this f of ck as the height of a rectangle. xk minus 1 is the width of that rectangle, and so each one of the terms in this sum represents the area of a rectangle. So in that context, this thing is saying that if f is continuous, there's some number I, so that if you choose the endpoints of those subintervals according to the recipe on the bottom, the total area of those rectangles added together will differ from I by less than epsilon for any number epsilon. Okay, so that's the theorem that we're out to prove in this section. Let's start by kind of establishing some terminology that we'll use as we walk through the chunks of the proof here. Okay, so those numbers that we pick between a and b that are a sequence of strictly increasing numbers starting with a and ending with b, they form a finite ordered set of numbers between a and b, and that finite ordered set of numbers, I'll just denote it by kind of an ordered n plus 1 tuple, and it's called a partition of the interval. All right, so choosing those x's is called partitioning the interval. And that partition divides our interval into non-overlapping subintervals. Okay, so there's sort of the one between x0 and x1, the one between x1 and x2, and so on. So those n plus 1 numbers x sub k goes from 0 to n, divides the interval into, I can be more specific, it divides it into n non-overlapping subintervals. Okay, Well, non-overlapping in the sense that the interior of them, of course, the intersection's not empty. Like x1 is in the first and the second subinterval, but that's the only point. So when I say non-overlapping, I mean that there's no the intersection of any two of them has empty interior. Okay, so some more terminology. I'm going to look at the widths of all those things, the width of the first subinterval, the width of the second subinterval, the width of the nth subinterval. Look at them all. The biggest one, the largest number in that set of n numbers, is called the norm of the partition. And I'm going to denote it with that kind of decorated absolute value sign. Okay, so the norm of the partition is the width of the widest subinterval in the partition. And the numbers, the C sub k's, the author chose of our text decided to use this Greek letter C, so I'm going to try to write it nicely for you. You pick those numbers in the kth subinterval. They're called tags. Sample points is another phrase you might see, but I'm going to call them tags in this lecture. Okay, so if I take the collection of subintervals, that is the partition P, together with the tags, I'm going to call that a tagged partition, and I'm just going to denote it by putting a dot over the P. Okay, so if P is a partition, if I write a dot over it, I mean I've selected a tag in each one of its subintervals. Cool. Little more terminology. That sum that we looked at above, where you plug the tags into F and multiply it by the width of the corresponding subinterval and add them all up. That's called a Riemann sum of the tagged partition. Okay, I'm going to denote it by SFP dot because that's what it depends on. This Riemann sum depends on the function, it depends on the partition and the tags that you pick. Okay, so I'll just denote it by SF of P dot. Those are the quantities that it depends on, and it's called a Riemann sum. Riemann after the mathematician George Riemann, although these ideas were attributed to Koshi much earlier. I don't know the history of why it's not called a Koshi sum. It's called a Riemann sum. Riemann kind of took these ideas a little bit further than Koshi later on in the history of mathematics. Okay, so in that terminology, let's just kind of rephrase, sorry about that, Koshi's theorem. So in that kind of brand new terminology, maybe you want to stop for a second and kind of review it, because I'm just going to start using it now. But here's what Cauchy's theorem is saying. If you take a continuous function on the closed interval, there's some number I, so that for every epsilon, you can find the delta. I'm emphasizing that delta depends on epsilon, such that the Riemann sum, SFP, of the tagged partition differs from I by less than epsilon for every tagged partition of the interval from A to B whose norm is less than delta. Okay, so if f is a continuous function, once you choose epsilon, you can find some delta, so that no matter how you pick a tagged partition P dot, as long as its norm, the width of its widest subinterval, is less than this number delta, then that Riemann sum will differ from this number I by less than epsilon. So Cauchy's theorem that says such an I exists. And I'm going to try to prove that to you here. Okay, so before we launch into the proof, I'm just going to try to like bust out some of the kind of core ideas of it. Okay, so breaking it into kind of smaller bite-sized pieces. So here's sort of our first attempt at that. So I'm going to work with some partition P. Okay, so take some partition P, and then let's choose some very special tags. If I write C sub k upper star, this should remind you of my extreme value theorem notation. I'm going to pick that number in the kth subinterval so that it's an absolute maximum for f over that kth subinterval. Okay, so that upper star, just like in our proof of the extreme value theorem, it's an input that gives me the largest output on that subinterval. Likewise, C sub lower star, the subscript k has to be there. So I don't think it looks that great either, but C sub k lower star, well, that's an absolute minimum for f over the same subinterval. Okay, so these are very special tagged partitions. I use the absolute maximum times the width of the subinterval and add them up. I'm going to denote that by capital M of the partition. So the partition, remember, is just the selection of the x's. So when I choose these C upper stars as my tags, I'm going to call that capital M of the partition, It's called the upper sum. The upper sum. It's sort of the largest of all Riemann sums because I'm using the absolute maximum for the tags. Likewise, lowercase m, I use the C lower stars times the width of the subintervals. I'll call that the lower sum. Okay, so because over each subinterval, I'm using the absolute minimum and absolute maximum, it would follow that any Riemann sum for any tagged partition would always be at least that lower sum and no more than the upper sum. Probably a good place to stop the video and convince yourself that that's true if it's not clear as I say it. But this lower sum is the smallest of all possible Riemann sums for the partition P. The upper sum is the largest of all possible Riemann sums for the partition P. Any other Riemann sum, any other choice of the tags would fall between them. Cool. Okay. So here's a little bit of a lemma about partitions, tagged partitions. Suppose I pick one. So I pick some tagged part, or some partition rather, excuse me, some partition of the interval from A to B. And then I pick another one in a very special way. I basically use all the same points that are in P, except I insert this new point. Can you see it there? Y, all kind of highlighted in green so you can focus on it. I insert Y and I do it strictly between xk minus 1 and xk. Okay, so I construct this new partition from P by using all the same old points, but I insert a Y that's in the interior of that kth subinterval. So that gives me some new partition. It's got one more point in it, right? So what the lemma is saying, it's really saying a couple of things. First of all, it's saying that when you do that, the lower sum cannot decrease. Okay, so the lower sum of the partition Q has to be at least as big as the lower sum as the partition P. Lower sums, when you stick a new point in, cannot get smaller. And likewise, upper sums cannot get bigger. Okay, so those are the kind of two main statements of this lemma. There's another statement in here that the lower sum for Q is less than or equal to the upper sum for Q, but that would be true for any partition, right? Because of what we said above. The lower sum is always less than or equal to the upper sum. So the blue thing, I'm throwing it in here, but really the gist of the lemma is that lower sums cannot decrease, upper sums cannot increase when you throw a new point in there. Okay, so how are we going to prove that? Well, I'm just going to kind of schematically draw this out. So I'm listing my partition subintervals here, P. It's got a first subinterval, second subinterval, so on, kth subinterval, down to the last one, the nth one. Pick some tags. Column C, C sub 1 through C sub n, and in particular, pick them to give the absolute maximums, okay? So I'm picking those CK stars to be absolute maximums over the kth subinterval, k from 1 to n. So like the notation above. Okay, and now when I look at this partition Q, well, lots of the subintervals in Q are the same, right? The first subinterval is the same, the second subinterval is the same. It's only this kth one that we broke into two, okay? So in all the subintervals that are the same, pick the same tags, the absolute maximums. And in fact, in these two new subintervals, I'm also going to pick the absolute maximums. I'm just going to call them alpha upper star and beta upper star. Okay, so I didn't write it here, but be sure you stop the video. Oops, sorry about that, and make sure that you're following what my idea is here. That I'm choosing this alpha upper star so that f of it is the largest output in the interval from xk minus 1 to y. Beta upper star is the largest output in the interval from y to xk. Okay, so it's like that extreme value theorem notation, and I'm just using some other Greek letters, alpha and beta here, because I'm just doing it on this one subinterval, and I don't want a double subscript. I could have called this C sub k1 and C sub k2 or something like that, but it's easier on my eye to just call it alpha and beta. Okay, so what am I going to do with those things? Here I have written it, that because, let me leave these things visible here. So the largest output on the interval from xk minus 1 to y cannot be any more than the largest output on the interval from xk minus 1 to xk, because the interval from xk minus 1 to y is a subset of that interval from xk minus 1 to xk. Okay, so I've written that down here, that f of alpha upper star cannot exceed f of c upper star. C upper star is the maximum in the input that gives the maximum over this whole interval. So in particular, that input would give something greater than or equal to the maximum over this subinterval. Likewise for the beta, f upper star of beta cannot exceed f of ck upper star, because the interval from y to xk is a subset of the interval from xk minus 1 to xk. All right? So if we looked at just the kind of relevant part of the Riemann sum, I'm skipping a lot of the Riemann sum over Q. So let me kind of write maybe here that if I was looking at that Riemann sum for F over Q, it would have a bunch of terms in it. And then I would get this term that corresponds to the subinterval from xk minus 1 to y, plus the term from the subinterval from y to xk, and then, there would be a bunch of other terms. So sort of just temporarily look at this line that I just drew, saying that the Riemann sum over all of Q would have some stuff, same exact terms that are in the Riemann sum for S of F over P, except it would differ in this interval that we split into two. Okay. But now I'm saying, we said above that, well, this number f of alpha star is less than or equal to f of ck. Same for f beta. So that's what I did, is I just replaced those things with the numbers that are bigger than them. That's why that made that bigger. So now we kind of, to follow these inequalities, you have to sort of ignore this. I'm only talking about the terms in the middle here. All right. Factor out that f of ck star, do a little bit of algebra, and you end up getting the corresponding term in the Riemann sum for F over the partition P. Okay, so what is that going to show? That's going to show that upper sum, because that's what we're using this particular tagged partition for Q here. So this would be the upper sum for the partition of Q. That upper sum is going to be no more than the upper sum for P, because these terms that we looked at satisfy that inequality, and the rest of the terms are equal. Okay, so that proves that capital M of Q is no more than capital M of P. I'm going to leave it to you to show that capital M of Q is at least, lowercase m of Q is at least lowercase m of P. So that proves the lemma. Okay, so just kind of recapping what the lemma says, when you stick a new point into a partition, that new partition's lower sum has to be at least as big as the old one, and the new partition's upper sum is no more than the upper sum of the old one. Or said more even briefly, that when you stick a new point in a partition, lower sums get bigger at least, and upper sums get smaller at least. Okay. I'm going to kind of leave it to you to say, if you did this for any number of points, if you added any number of points to the partition P, the upper sums cannot increase and the lower sums cannot decrease. So adding points to a P, people usually, or to a partition P, people call it refining the partition. So when you refine a partition, you can only make the upper sums smaller and you can only make the lower sums bigger. Okay. That's one lemma. A second lemma, which I'm not going to include a detailed proof of, this lecture is going to be long enough, and we could have done this in the past. It's called Cantor's intersection property. And so it says if you take a decreasing sequence of closed intervals, so one closed interval contains another, which contains another, and so on, and the width of them, the distance between the endpoints, is going to 0 as n goes to infinity, then there's some real number I that the sequence of left endpoints and the sequence of right endpoints both approach. Okay, so I'm not going to include a detailed proof of that thing here in this video. It'll get way too long. But you can go back and just sort of modify the Bolzano-Weierstrass property argument that we gave in our location of roots theorem. If you kind of look at that, that's an alternate proof. In fact, if you look at the proof of the location of roots theorem in our text, they basically use this Cantor intersection property to do that. Okay, so you can sort of just modify that. Basically, you can argue that the sequence of left endpoints is a sequence in the closed interval from A1 to B1. It's got a convergent subsequence and so on. And then you use this condition to show that the corresponding subsequence of right endpoints converges to the same limit. Okay, but that's all the detail we'll go into here, because let's keep focusing on Koshi. Now we're armed for the proof. Okay, so we know kind of what we mean by a partition. We know what we mean by upper and lower sums. We know that if we so-called refine a partition, that lower sums can only get bigger and upper sums can only get smaller. All right, so that's kind of just recapping. So here we go. Let's walk through the proof of this thing. Stop the video a lot and think about in detail a lot of the statements that I make here, and sort of bullet point by bullet point. Another thing I'm going to recommend is when you're done watching this video to stop and sort of make your own kind of bullet point style outline of like, what were the major components of this proof? This is a fairly long argument, but if you break it down into kind of its principal components, each one of them you can sort of digest, and then you can kind of start trying to understand the whole argument in terms of these pieces. Okay, it's not just in this theorem, but that's good advice in general. Okay, so let's take our continuous function on this interval a to b. And we know that a continuous function on a compact set, the closed bounded interval, is uniformly continuous. That's theorem 548. So if it's uniformly continuous, if somebody gives me some epsilon, I can find a delta that depends only on that epsilon. So I'm going to continue to focus on that notation. Delta of epsilon means what I'm applying it to. So there's some delta, depends only on epsilon. So that if I take x and y close enough, and here I'm going to be applying it to the number epsilon over b minus a. So that's why I'm writing that delta of epsilon over b minus a. If the inputs are within that distance, then the outputs are within epsilon over b minus a. B minus a is a positive number, so given epsilon divided by it is a positive number. Okay, so that's by uniform continuity. So, given this epsilon, I have this delta that depends on epsilon over b minus a. If I take a partition whose norm is less than that delta, which I could always do, right? I mean, if you want, you could take the partition so that the endpoints are equally spaced. And once you decide what this delta is, this delta of epsilon over b minus a, just choose the number of points in the partition large enough. Say if you're going to use n points in the partition, just choose n large enough so that, b minus a over n is less than this delta. Then you're guaranteed that the maximum width of the subintervals will be less than delta. Okay, so you take some partition whose norm is less than our delta, and I mean delta of epsilon over b minus a, but it's easier just to say delta. Okay, and then by uniform continuity, well, if you take 2 points that are closer than delta, the outputs are closer than this epsilon over b minus a. Well, the C upper star and C lower star, those come from the kth subinterval. Any 2 points in the kth subinterval are closer than delta to each other. So I know that the absolute value of the difference of those two outputs is less than this epsilon over b minus a. But in this case, those absolute values aren't doing anything because the absolute maximum value is always greater than or equal to the absolute minimum value. So that difference is greater than or equal to 0. So I don't need to write the absolute values. Okay, so summarizing, take a partition whose norm is less than delta, then for any k between 1 and n, the difference of these absolute maximum and absolute minimum values is less than epsilon over b minus a. Cool. Well, if that's true, then I could multiply both sides of this by both sides of this inequality. For each k, I could multiply both sides by xk minus 1. It's a positive number, right? And then I could add all those things up and I would still have a strict inequality. So that's what I've got on the next line. I just take that difference of those function outputs and multiply it by the width of the kth interval and add them all up. But every one of those things is less than epsilon over b minus a times the width of those subintervals. So same for the sum. Okay, but this sum on the right-hand side, epsilon over b minus a, is a constant. The width of the subintervals is certainly going to add up to b minus a. So that sum is just going to add up to epsilon. If I distribute the width of the subinterval through this sum and rearrange it, well, the f upper star ck's times that width is our upper sum, and the f lower stars is our lower sum. Upper sums are always greater than or equal to lower sums, so that difference is non-negative, and the inequality above says that it's less than epsilon. Okay, so to summarize, if P is a partition whose norm is less than this delta, the delta constructed from this epsilon over b minus a, then the upper sum for P minus the lower sum for P is non-negative but less than epsilon. Okay, so that's a stopping point. I can do that for any epsilon. I can do that for any epsilon. So I'm going to do it for some strategic epsilons. I'm going to pick a sequence of partitions. Let me tell you about P1. For P1, I would take epsilon to be 1. And there's some, or actually, I guess not 1, but I would pick it so that it's sort of I want 1 over b minus a to be 1 over n. So I would take epsilon to be b minus a times 1. All right. And then I would, so in other words, I want the norm to be less than delta of 1. And then I would pick P2 to contain all of the points in P1 and also make sure that its norm is less than delta of 1 over 2. And then pick P3 to contain all of the points of P2 and its delta, its norm is less than delta of 1 over 3, and so on. So I would use the above construction to create a sequence of partitions so that each one contains all the points of the previous one, and their norms are less than delta of 1 over n. All right, so I'm basically taking the epsilon, so that I can't quite do this algebra in my head. I want the epsilon over b minus a to be 1 over n. All right, so you can take epsilon then to be b minus a over n. That's what I was choking on earlier. So take for each n, I take an epsilon to be b minus a over n and apply the construction above to get this partition. And then I always select the new partition to contain the one before it. So they're refinements. All right. So by the construction that we just went through above, if I look at the upper sum minus the lower sum of that partition, it's non-negative, but it's going to be less than 1 over n. Okay. It's my epsilon. Cool. Okay. So our first lemma says that when you refine partitions, lower sums can only get bigger and upper sums can only get smaller. So for every n, we have this sequence of inequalities. I'm not going to try to pronounce it, but that's from lemma 1. Okay, so that means that the intervals between these upper and lower sums for this sequence of partitions are nested. The first one contains the second one, which contains the third one, and so on. So I'm going to leave this as a little exercise to you. If at any moment that interval has width 0, so the lower sum for this partition and the upper sum for this partition are equal, then in the statement of the theorem, you can take I to be that number. Okay? And then it will be the case that for any partition whose norm is less than the corresponding, for any epsilon, you can find a delta, so that any partition whose norm is less than delta, that difference is going to be less than epsilon, because you can actually arrange for that Riemann sum to equal this value I. Okay, so there's some details there that I'm going to leave to you. But if it's ever the case that these intervals shrink to width 0, then as soon as it happens, you can just take the lower and upper sum that are equal, take that to be I, and it'll satisfy the condition of the theorem. I'm going to leave the details to think through for that one to you. Okay. If it's not the case that any of those limits or any of those intervals are going to 0, then we apply Cantor's intersection property. Cantor's intersection property says that the left endpoints, the lower sums, and the right endpoints, the upper sums, are approaching the same number. Let's call that number I. Okay, so now I'm going to prove that that I satisfies the condition of the theorem. So pick an epsilon, and by the uniform continuity, let's take a tagged partition whose norm is less than delta of epsilon over 2. Okay, so we know that the upper and lower sum of that particular partition differ by no more than epsilon over 2. And if you pick any set of tags over that partition, then the Riemann sum for that tagged partition, this thing I'm writing in the middle, is just F for that set of tags. It's got to be at least the lower sum, but no more than the upper sum. Okay? So now choose a number, capital N, a natural number that's bigger than 2 over epsilon. And just as a special case here for a second, let's suppose that the interval between the upper and lower sums for our partition up there and the upper and lower sums for the partition P sub capital N as constructed earlier in the proof, suppose there's some point that's in both of those intervals. So the intersection of those intervals is not empty. All right. Well, by the construction, and you have to kind of think through all the details in this, it's a long story, but our number I, it's the limit of these sequence of endpoints of these P sub n's, lower and upper sums of the P sub n's, it belongs to the interval between the lower and upper sum for P capital N. That's by construction. And the width of that interval is no more than 1 over n, again by construction. So this number I belongs to this interval, and the width of that interval is 1 over n, right? I'm going to scroll back so I can see it. Our Riemann sum belongs to this interval, and the width of that interval is no more than epsilon over 2. Okay, and we're supposing that we have some number in both of these things. So our Riemann sum is within epsilon over 2 of that number, and I is within 1 over n of that number. Okay, so by the triangle inequality then, our Riemann sum and I can be no more than epsilon over 2 plus 1 over n. Cool. But 1 over n, this is why I chose n to be bigger than 2 over epsilon. 1 over n is less than epsilon over 2. Okay, so in the case that these two intervals have a point in common, then any tagged partition whose norm was less than this delta of epsilon over 2, which comes from the uniform continuity, its difference from I is less than epsilon. So the condition of the theorem is true. Good. So the proof will be concluded if I can convince you that it's actually always the case that those two intervals have something in common. All right. So I've got this partition P and I've got this partition P sub n, and I want to show you that those two intervals have something in common. Well, take Q, to be the union of those two partitions. Just union them together. Throw all the points in P and all the points in Pn and arrange them in kind of increasing order. If there's any duplicates, then just use them once. Okay. Then if you take any Riemann sum over Q, I claim that it belongs to both of those intervals above by lemma 1, right? Because Q is a refinement of P. So that means that the lower sum for Q, M lower Q, is at least MP, and the upper sum is no more than capital MP, right? So that interval, little mq, capital MQ, is contained in this thing, and there's something in it. But Q is also a refinement of Pn, so it's also contained in here. So anything in that interval between little mq and capital MQ is going to be in both of these intervals. So those intervals are never disjoint. Okay, so the case that we proved above that finished the theorem actually has to hold. So these things are never disjoint, and that completes the proof. Whew. It's a sophisticated argument. Definitely lots to think about. I hope in class we'll have time. If you watch this before class, it'll be good because we can just kind of focus on questions about the details. So I'm going to end. This video is kind of long. I'm going to end by saying that this number I in Cauchy's theorem has a name. It's called the definite integral of f over the interval from a to b, and it's typically denoted like this. Looks familiar from calculus books. In more advanced books, it kind of just gets denoted like that. The thing is still called an integral sign, but we kind of throw out the of x and the dx because, well, what does this number depend on? It depends on f and the interval from a to b. So why put any more notation in it than that? All right. So I'm going to leave it as an exercise to you to show that this thing's value is unique. Okay. So Cauchy's theorem says that there exists some number I that satisfies the condition of the theorem. And there's only one number that satisfies that. Given a continuous function f on a closed interval from a to b, if two numbers satisfy the condition of Cauchy's theorem, then they're equal to each other. And I'm going to leave that as an exercise to you. Okay, so this was a long one. I hope that was useful to watch, and thanks for listening.